So you typically overflow a buffer, keep going, you would cause some exception to get thrown, and then the exception mechanisms would go and loop on the stack for exception metadata to tell it where the exception handlers were. Now, because the exception handler metadata was on the stack, that was part of what the attacker has corrupted with his data. And therefore, when the system jumped to an exception handler, or what it thought was an exception handler, it was actually jumping to attacker data. So again, we kind of tried to respond to those by improving the GS mitigation in the compiler. So now, as well as placing a cookie between the local variables and the return address, we'd reorder the local variables. So all the things that seemed really dangerous, like character arrays, we would put right up next to the cookie. So by overflowing a character array, you'll never end up crashing another local variable. We also added safe SEH, which meant that the compiler would perform extra checks before jumping to an exception handler. However, a lot of these were limited by the fact you actually have to recompile your code. So for example, with safe SEH, if you had a single module that wasn't compiled with safe SEH, and as an attacker you claimed that your exception handler was in that module, then the system had no way of knowing whether that was valid or not. The system sees, I'm jumping to an exception handler in this module that hasn't been compiled with safe SEH. So I've got no information as to whether it's a valid exception handler or not, and so I have to play safe and jump to it. So that was a common evasion of that version of GX. So that's kind of what's documented here. So you might have recompiled kernel 32 and then TDLL with safe SEH, but you've got some random DLL module that hasn't. And as an attacker, you just claim that your code is in there. Okay, so with Windows XP SP2, that was probably the most major kind of step change, as it were. We rebuilt all the system binaries with the GS version 1.1 and safe SEH. So that meant that from that point onwards, flaws in Microsoft code were going to benefit from those new mitigations. And we also introduced the first round of heap mitigations. So as well as stack overflows, it became evident by then that heap overflows were equally exploitable. And so we introduced new software depth in XP SP2. Another common problem from our point of view in terms of defending against exploits was that there were a lot of interesting pointers and objects that were at fixed addresses in the address space. So one of the common exploitation techniques was to overwrite data in the process environment block or the thread environment block. And those are always known to be at fixed places. So randomizing their locations helped reduce the reliability of an attacker's exploit. A number of fixed pointers we encoded with a random value, again to kind of reduce the reliability of someone just overwriting that pointer with the value of their choosing. So, whereas early on it was trivial to exploit any flaw, those mitigations did start provide kind of putting in place some hurdles for the attacker to overcome. But it's kind of a game of cat and mouse, and for every creative thing or every defense that you put in place, you're really just encouraging creativity on the attacker's part. So, you can kind of say, well, I'm not going to allow you to execute these pages on the heap, but then the attacker just has to find a way of somehow executing virtual protect to remove that read-only protection on those pages of the heap. So for example, the attacker would disable dep and then be able to run code on the heap anyway. I guess the main point here, though, is that you're kind of raising the bar. So whereas before, given a bug, you would be able to exploit it by default, you're now putting some obstacles in place. And whereas the scenarios in the past were completely unconstrained, you're now imposing constraints on the attacker. So sure, the attacker can still exploit a flaw, but only if he can also first call virtual protect, or only if he can first find suitable ways of disabling the relevant mitigations. Okay, so there's a whole bunch of people who've documented how to exploit XDSP2. I won't dwell on that. The slides will be available afterwards, and you're welcome to look up the references. Okay, Visual Studio 2005 is released, new version of the compiler. Again, a couple of improvements to GS. So we still do the GS cookie that protects the return address. We still reorder the local variables to prevent one of them corrupting another one. And then the other thing that we've done here, which is shown kind of on the left, is parameters that were passed into the function. During function execution, we'll make a copy of those at the other end of the stack. Now the purpose of that is kind of like the local variable reordering. Suppose an overflow happens from these local variables. It corrupts the cookie, the return address, and these parameters that were passed in. Now a function exit, because the cookie's been corrupted, will terminate the process. But the function might be doing a whole bunch of things before it exits that makes use of these parameters, and we really don't want corrupted values being used. So that's why at the start of the function, we just make copies of these parameters and use those values during execution. So even if a buffer overflow has happened, then while that function is executing, we'll use the saved copies we made. And then when the function exits, we'll detect the overflow by the fact that GSPT has been corrupted. There are also some other minor improvements. Strict GS was a pragma that made GS very aggressive and protected a lot more functions. We'll come back to that. Which has a number of vulnerabilities associated with people using the operator new. So you would allocate n objects of size s, say, with new, and the actual total size of